Okay, let's talk about one of the sorting algorithms, bubble sort. Bubble sort is a name given to an algorithm where the highest number bubbles up to the top of the list or the end of the list. When you watch bubble sort operate, you'll see certain numbers moving towards one end or the other of a list. This is where the name comes from. The large numbers tend to bubble up to the top. So what we're going to do is we're going to create a simple version of bubble sort. This is not an optimized version. This is actually probably the worst version. But the purpose here is to demonstrate how we analyze an algorithm and how we can improve an algorithm and how we walk through talking about a sort algorithm. After we make the bad version, we will try to make a slightly better version that has and exhibits adaptive behavior. So let's get started and walk through our version of bubble sort. This is our algorithm. Given a list of n items that are unsorted, we want to process and walk through each item in the list, and we're going to compare it to its neighbor. If the neighbor is smaller than the current item I'm on, I'm going to flip their positions. So large numbers will tend to move up the list and small numbers will tend to move down the list. I will continue to do that until I get to the end of the list. So I've compared the n minus 1 item to the nth item. Now with bubble sort, that will not guarantee that the entire list is sorted. That will only guarantee that you've moved some of the things around in the list. So we have to repeat that entire loop over again. And you have to do it n times if you want to guarantee that the entire list is sorted. So here in pseudocode, you can see the algorithm we've just talked about. We're going to loop through an outer loop n times, and for each of those loops, we're going to go down the length of the list, comparing adjacent items, and swap them if they have to be swapped. So let's see how that looks. Here we have a list with 6 items in it, so our n is going to equal 6, and you can see that it's in somewhat of a random order. So in order to implement the algorithm, we need to start with j, our inner loop, equal to 1, and we're going to go up to n minus 1, or we're going to go to 5 times. So in our very first iteration, we need to look at the very first element in the list. So we're looking at item j, and we're going to compare item j to item j plus 1. So the blue box is representing the item j, and the green box is representing the item j plus 1. So our algorithm says that we now need to look at this and decide, is item j plus 1 less than item j? In this case, we'd be comparing if the green box item is less than the blue box item. In our case, is 3 less than 4? The answer to that question is yes. Then we must swap them. So you can see that 3 and 4 switched places. And now I need to go to the next j. So j now needs to move up 1. J is equal to j plus 1. And I'm ready to do this over again. So you'll see that I've now, when j is equal to 2, I've copied the results from the previous row. So 3 and 4 have switched places, and I've now moved over 1. I'm now looking at 6 and 4. If 6 is less than 4, then swap. It's not, so I don't swap. I go on. Is 8 less than 6? No, don't swap. Move on. Is 1 less than 8? Yes, swap them. You'll see that the 1 and the 8 have swapped places, and I need to move on. So now I'm looking at, is 9 less than 8? The answer is no. And I've now arrived at j equal to n minus 1, or j is equal to 5. So n is 6, so j is now equal to 6 minus 1, or 5. So we've actually compared all of the items in the list. And if you look at the list, it's not sorted. We're still in this order of 3, 4, 6, 1, 8, 9. So what do? We start over again with j equal to 1. You'll notice that this particular run through our list took n minus 1 comparisons. Keep that in mind. When we analyze the algorithm later, we're going to kind of add up all of those comparisons. So let's do it again. J is back to 1. We now have our list from our previous iteration through. And we do the same thing. Is 4 less than 3? No. Is 6 less than 4? No. Is 1 less than 6? Yes, swap. Is 8 less than 6? No. Is 9 less than 8? No. And you'll notice that the two largest numbers are now at the end of the list, 8 and 9. In fact, the three largest numbers are 6, 8, 9, but we haven't really gotten to the point where we can say that 6 is in the right spot yet. So what do? We repeat again. I'm not going to walk through every single iteration here, but we'll do it in summary. Here's our original list. After the first run through the list, remember I is counting the outer loop, so we've gone through the outer loop one time. This is what the sort looks like. After we've done it a second time, this is what the sort looks like. We would then do it a third time, a fourth time, and you'll notice after 4 times, our list is sorted. But our algorithm has nothing built in to say we're done. It's looping 6 times. So we would have to do the 5th loop and the 6th loop. Nothing changed, but we still had to do them because our algorithm said to run through this n times in order to be guaranteed that the sort will be complete. So, once again, remember, for each time through the loop, it did n minus 1 comparisons. So I can now say that overall, this process took n, the I loop, times n minus 1 comparisons, the j loop, or this is of the order of n squared. You may say, wait a minute, it's n squared minus n if I multiply that product out. But when we are talking about asymptotic behavior, when we're talking about big O notation, we're talking about the dominant term in n. In this case, n squared dominates over n when we go to very large n's. Here you can see the path that 4 followed through the system. You can see that the 4 on each pass moved up towards its final position in the ordered list. This is true if you follow any number. It will generally, large numbers will move to the right in the path. Just like if we follow the 1 path, it moved towards the left in our stages and ended up in its final position. You can trace paths through the data in this way to give you sort of an idea of how the algorithm is functioning. What would happen if we had a pre-sorted list with bubble sort version 1 algorithm? Well, as we kind of saw at the end of our previous example, this list gets sorted 6 times because there's 6 items in the list. So we're going to run this thing 6 times regardless of whether we had to make any swaps or not. That is not very efficient. So problems with our bubble sort version 1. It runs in n times n minus 1 time asymptotic behavior. That's order of n squared. That's not very good. Generally, you don't want to follow sorting algorithms or use sorting algorithms that have n squared behavior if you're going to do any sort of large size sorting. It also runs that whole n times n minus 1 times even if the list is already sorted. There's no adaptation to the data. So what we'd like to find is an adaptive sorting algorithm that can end early if there's nothing more to sort. Thus is born bubble sort version 2, the adaptive version. There's one little minor change we have to make to our algorithm. So what we keep track of is if any swaps were made or not. If there were no swaps made, then we can stop. We're done. We've already got the list sorted. So you'll notice that the only addition to our algorithm is now we repeat this entire process if a swap was made up to n times. If the swap is not made, then we want to end. So in our pseudocode version, that is added in here with the swapped equals false, swapped equals true, and if swapped equals false, break out of loop lines in our pseudocode. Swap will be false as long as no swaps were made, in which case the outer loop will break and will be done early. See how that works. Here's our original sorted list. Were swaps made? Yes. Were swaps made? Yes. Were swaps made? Yes. Were swaps made? No. End. So we now did n minus 1 comparisons 4 times. So now we did it as n minus 2 times n minus 1 times. You'll notice that's still order n squared. You say, wait a minute, it's supposed to be better. Well, it is better in this actual application for this particular case, but its overall asymptotic behavior is still going to be n squared. That's a reality of bubble sort. You're looping through a nested loop algorithm, so you're going to get n times n as the dominant term. But the adaptive version certainly works better. It ran here in less time than the original version. And if we do it to a pre-sorted list, we look through this list and say, was there anything to swap? No, end. So in this case, it would have ended in a single run. So the adaptive version is definitely better. So let's look at the overall pros and cons of bubble sort. The pros, it's an adaptive algorithm. If the data is already sorted, it will end very quickly. It's an in-place algorithm. This means that there's no additional storage needed. So if you have 10 million items, the sort will take place in the storage location of those already allocated 10 million items. You don't have to allocate additional storage. That's an advantage. It's a stable algorithm, and it's simple. It's easy to implement. It's easy to understand. It's easy to pop into your program off the top of your head. Now, are any of these pros enough to outweigh the fact that it has order n squared comparison and swaps? Probably not. If you're only sorting 5 or 6 things, who cares? It doesn't really matter which algorithm you use. The overhead of creating fancy algorithms may actually be more than simply doing the bubble sort a few times. But if you're sorting any sort of reasonable number of items, bubble sort will begin to fall behind quickly because it's an n squared algorithm. But what algorithm you choose for sorting is always up to you, and you have to weigh all the factors present.